also reflected here in this kinetic part of the tone. So now coming back to the effective interaction, we can plot this. We have seen this picture already a couple of times. I didn't know that when I prepared the talk, so here it is again. This is the 3D version. This is the 1D cut of this 3D version. What you have here in the center, or here, is the Coulomb attraction. It's the singularity at the origin. And then what else? Then we have the cut of the Coulomb potential by the dashed red here. And then we have, say, field times z. If the field is directed along the positive z direction, it's this one here. And then out here, you see that the Coulomb potential is small, therefore this asymptote is determined by the Fz term, and likewise here it's determined by the Fz term. So this is the effective potential, and under particular circumstances or conditions, I form this effective barrier through which the electron can travel. So this is the problem that we will look at today. Later in the talk we will add nuclei to this problem. So when is this applicable? This we have not discussed well, it was mentioned earlier today also. Now I give you the original argument here provided in the paper of Kelgish. So we look at this problem again. Let's introduce some new symbols here. This we like as theoreticians, of course. So the ionization potential will now be called kappa squared half. Let's determine the exit point here. As you see from the figure, at the exit point, the Coulomb potential is small compared to the Fz term. At the exit point, I therefore say that the potential is dominated solely by F times Z naught, where Z naught is the exit point I want to determine. And you see here from the figure that this Z naught should be equal to the ionization potential. From this, I isolate Z naught, the exit point. Now, classically, you would say, how long time does it take for an electron to reach that point Z naught? Well, it takes the distance divided by the typical velocity, which is the same as this kappa here in these atomic units. So this is the, so to speak, the time it takes for the electron to go here, to go from here to here, in some sense, which I will not specify. And then we have here a typical timescale for variations in the external field. So if this omega is the frequency, 1 omega is the timescale, 1/2 is the timescale for when the field points in positive z direction compared to negative z direction. Then I can form this ratio between the time it takes the electron to go to this exit point and the typical timescale of the field, and plugging in these symbols here, I end up with this so-called Kelgish parameter, which in these symbols is the frequency of the field kappa over F. So what we see here is that if now I have a small frequency or a high field, this number can be very small. What does it mean? It means that the field, so to say, points in this direction, positive z direction, for a long time compared to the electronic motion. This is the physics of this. If that condition is fulfilled, that this number is much more than 1, you will find statements like the electron has time to tunnel before the field changes direction. So this is the field, this is the regime we're interested in. In fact, it's not enough that this gamma here is smaller than 1 to apply a tunneling theory. You also need, of course, that somehow the energy in the field compared to the ionization potential should be much smaller than 1. Because if this is much more than 1, the time scale of the laser variation is much slower than the time scale of the electron motion. And then in this regime, the field is an adiabatic changing external parameter, and you can use adiabatic theory. And that's a theoretical justification for using tunneling theory to describe processes happen in a time domain. Questions to this? That's clear. Then we can look at the problem again. Here's my system. I apply the field in the positive z direction. If the system breaks up, the electrons will fly in this direction, the nucleon will fly in this direction. Then I put something here, and this means, well, I'll come back to this on the next slide. When you have such a system here which fly apart, we solve the Schrödinger equation without going away boundary conditions. And this turns the problem into something which is called the Seeger problem or Gamow state problem. And this means that the energies are no longer real, but the energies in the field are complex with a real part and an imaginary part, which is related to the rate of tunneling. So there's a big literature on this type of stuff. You can see this is like a width of the state, and it corresponds to the tunneling rate.
I might be getting a little bit ahead of where we are, but how important is it that you're not considering the nuclei to be stationary?
At this point, it's not. This is completely general. This statement is true when the nuclei do not move, and also true when they move.
Okay.
It's just, of course, much more difficult to solve when the nuclei move.
Well, right. It's to say I see your graph, and I immediately think to myself, if I was to try to make a simulation of this, I would not have moving nuclei. I would have to fix.
Yeah, well, that's of course a valid approach, but it's often wrong.
Okay.
Yeah. Oh, there are cases when it's wrong. At least you have. This we will discuss in detail later, but I can say now that under some conditions it's very wrong. Under other conditions, you have to at least include some nuclear motion in some Oppenheimer way, or maybe by some averaging over some vibration ground state waveform. So anyway, here I write in text what I just told you, that when we solve this equation with outgoing wave boundary condition, it creates these Seeger states or Gamow states. This is something which I have found is not well known. It's kind of standard quantum mechanics courses. It's not really described. You can find excellent pedagogical papers on this type of stuff in American Journal of Physics. And you can also, if you like, try yourself to solve a problem like this, 1D problem, 1 degree of freedom x, and then you can try and build such a rectangular potential. And how to set up this problem, I'll just sketch it here, and then you can try yourself, and I'll be happy to assist you. Here, of course, you can have waves going both ways. Here you will have waves going both ways, but here you only have outgoing waves. This is what it means to have outgoing wave boundary conditions. And then you will see, when you do this, that you get a complex solution. Here, we don't want, of course, when we do the theory, we solve such problems ab initio the right way, and this involves typically some arming propagation techniques and other things. This I will not go into detail in this talk. I'm rather focused here on the analytical approach, and to do that, let's just discuss a little bit the strategy here. The strategy here is maybe, it could be illustrated in this kind of model system, but let's just try and illustrate it straight away in the real physical system, where we somehow assume that I have the field along the z direction. So here's the field again. This is the z term. I have the Coulomb potential somewhere here. Oops. And then I build the effective potential like this. And now I consider this state here. In tunneling theory, when we do the analytical approaches that I will discuss, we assume that the ground state is not really much affected, at least in the leading order theory. So we have some ground state here, and then the whole trick is to match here in this region under the barrier to a solution which is outgoing out here, but continuated into this classically forbidden region. So now I gave you already the steps, and I will come back to these steps later in the talk and make this more clear. But the idea is that you have a bound state which has already a tail out here in a region which overlaps with an outgoing wave. Okay? This, of course, this picture you can also try and use here in the analysis of such a
Excuse me.
Yeah.
I'm a bit confused by this complex energy solution. So
Yeah.
the Hamiltonian is supposed to be Hermitian, right? And
But when you impose those outgoing wave boundary conditions, it's no longer Hermitian.
Okay. And what?
Yeah, this I cannot go into more detail now why this is the case. Then we have to sit and look at this carefully together. Maybe someone else has a good comment at this point.
Well, I thought that the operators had to be Hermitian because only Hermitian operators are observable. And if it's a complex energy solution, then the full solution isn't going to be observable anyway because we can't observe imaginary values. So I think that's the
within the uncertainty principle, yes, you will not be able to observe it, right? Within the, I mean, this is the whole idea of having a decay time or a decay lifetime to these things.
But the Hamiltonian does not have a stationary solution at those energies. But you have
I know how this
part of the outgoing complex wave function is affected by these excited states of energy.
No, but I think that he's concerned that the norm of the wave function is not going to be conserved, which is just a physical statement that you lose your particles.
Yes.
That's really what it means.
This is what it means. The norm is, of course, decaying with exactly
Right.
this rate.
So that's part of the outgoing wave.
Yeah, exactly.
Right. And they cannot come back, so you lose your.
In some other, maybe you know some other examples in atomic physics where you have a similar but different situation. For
Well,
example,
spontaneous emission is the most famous example, maybe. Spontaneous emission.
Exactly.
Yeah.
Yeah. This is one example
Right.
which we all have had in some course at some point.
Right.
Yeah. But also, if you want to have a more exotic example in atomic physics, you can think about a double excited state or multiply excited state in some atom, which couples to a continuum also. So when you have a coupling to a continuum, you have this decay, and it's the same here because this is the coupling to the continuum because you can go through this barrier. So now let's look at the history of tunneling. This is now the tunneling rate in hydrogen. And here are some authors that worked on this in the 20s.
Right.
And here you have the tunneling rate. You see it is an exponent which involves the field. And if you look at how this F is, you will see that if the field is large, it's a larger probability for tunneling than if it's small. And all of these authors are correct, in fact, in the exponent. But only the last authors are correct in the prefab. So this I just show you because it adds to the history, but this is not a super easy problem. It's not traditional perturbation theory to get this kind of stuff out correctly. In fact, the first time this was done correctly was in this textbook of Landau and Lifshitz in the English version from '58. They discussed this, but of course it's probably not considered to be important enough to discuss in the main text. Rather, it's discussed in a problem. So the problem is to determine the probability of ionization of a hydrogen atom in the ground state in a strong electric field. And then there is also a sketch of the solution here. But this is in fact not so easy to follow. So yeah, this we will come back to. So more history on this. The theory that you need to apply here is asymptotic theory. It's this kind of theory that you need to apply to get this rate correct, because it's not conventional perturbation theory. It's called asymptotic theory, and it's an asymptotic theory that assumes the field to be weak. So therefore, we refer to this as weak field asymptotic theory. And the general structure of the rate will be a leading order term and some possibly correction terms. For spherical symmetric potentials, meaning atoms, Oppenheimer got this exponent right. Landau and Lifshitz got A, B, and C right for the hydrogen atom in the ground state. These authors got A, B, and C right for a general atom in an NLM state. These authors consider Stark states in hydrogen, special in parabolic coordinates, and got A, B, and C right, and even obtained some corrections. So this was pretty well understood relatively early on. Now, for arbitrary potentials for molecules, in our case, nothing was, not a lot of stuff was done, and that was probably mainly due to the fact that there was not so much experimental activity on molecules until maybe the 90s, initiated in particular from Paul Koch and his collaborators. But then a lot of experiments appeared, and there was a lack of tunneling theory for molecules. I want to highlight here the so-called molecular ADK theory, which is a tunneling theory for molecules, which cannot be derived rigorously, but which was put in the literature based on some intuitive, well-justified physical arguments, taking the atomic case and generalizing it to the molecular case. In fact, this coefficient here is wrong for polar molecules in the MOADK, and there's also some inconsistency in the way you structure the theory. So this was the situation. Then I have been involved in some works later, which addressed this problem and actually also solved it for the first time. So this is the main theme for this talk. And now you may also ask how can it be correct to say weak? Why is the field weak? Because we talk about strong field physics. And for this, maybe one way to see this is maybe to discuss a little bit atomic units. If I have an intensity of 3.51 times 10 to the 16 watts per square centimeter, this is the intensity that corresponds to one atomic unit of intensity. So if I now want to have some intensity in atomic units, I take this intensity in watts per square centimeter and divide by this I naught. Then I have the intensity, and then I get the field strength in atomic units as just the square root of the intensity in atomic units. Oops. So this is the way it's done. And as you probably know, typical field strength, typical intensities are around 10 to the 14 watts per square centimeter, meaning that this one number here is typically smaller than 1, significantly smaller than 1, leading to smaller than 1 field strength.
I thought the atomic unit of electric field is the electric field held by an electron in the ground state of hydrogen.
Yes, it's...
Which should be different from that.
Yeah, it depends a little bit on what factors you absorb here, because there is factors of 8 pi and epsilon. And this is one convention. This is like a convention. So many people follow this convention. And if you follow a slightly different convention, the conclusion will be the same. So the fields that are of relevance here are weak, because these are the fields that are used exponentially. Okay, so that's so now why was this thing about the molecule? Why was this difficult? One thing is that, for example, you have now 1, 2, 3 centers. So if now a 3 center problem instead of just a 1 center problem, that makes it more difficult. Furthermore, you have the complication that, as you see here, it seems that it's different if the field points this way than if the field points this way. Because if the field points this way, I drag the electrons to this side, and if it points that way, I drag the electrons to this side. So this is something we have to be able to describe. You also have start shifts here. This I denote here by this formula. So just this is interesting. You see, you have normal perturbation theory for the energy, but unconventional perturbation theory for the rate. The energy of a system in the presence of a field is the energy with no field minus the dipole times the field, and then maybe some polarizability induced dipole term. I think here you don't need to have this in mind. But if we just consider this, you also see that there's a different shift here. If the dipole is parallel to the field, I get a higher ionization potential than if it's anti-parallel. Let's just make a drawing of this also. It's kind of illustrative physically. I think we need some new pens for the rest of the meeting. Can you see what I write here? No. They're very weak, the pens. I try anyway. So now, if the field is 0, I have some energy. Now, I have a situation where the field is not 0. Then this will split up. I just draw this formula, or sketch the result of that formula, into 2 lines here, where the first one will be the upshift one corresponding to that the field, say, is in this direction, and the dipole is in the opposite direction. Right? Whereas this one, I have the field and the dipole in the same direction. And if this is the ionization threshold up here, you see that the ones that are anti-parallel with the field will have a smaller ionization potential, and it's the ionization potential that determines how easy it is to ionize. Right? So that's one effect. And so now, if we come back to that, we can, at least for the molecules, we have to at least use a generalization of the molecular ADK based on some adiabatic picture, namely include a kappa-dependent field, field-dependent kappa here, field-dependent binding by this type of form. And this is now this sketch here I illustrated. This is just for me to remember that I should make a background figure of the image. I have done this, I can continue. So now, and then after Paul's talk this morning, I wanted to illustrate one of his statements, namely that the direction of the field with respect to the system matters, and you can then take that into account, and you can get a long way with then subsequent classical propagation. Right? So you have a molecule, you have the field going around. If it's circular, for example, it's a circular field, you will have in one half plane, you will have the field parallel with the dipole. In the other half plane, you will have it anti-parallel with the dipole. So when the field points, say, in this direction, the energy shifts up. It's easier to ionize. So all the electrons that I ejected here, I ejected in one in this when the field points in that direction. And then if you do this classical calculation, which maybe you did already in the break for an electron in a circular polarized field, you will see then that this is enough to explain such an asymmetry in the photoelectron momentum distribution, which was observed some years ago. So in that work here, we had an orient OCS molecule and a circular polarized light, and the only thing that was needed to explain the main observable was an energy-dependent rate and then a classical trajectory. So this explains this So, but then there are also many cases where we don't, where we can't explain what we see. I don't want to go into detail here, but I just mentioned that in CO2 OCS, there are data where tunneling theory cannot explain really what is seen. So this, of course, can be due to the fact that the experiments are not performed in a regime where tunneling theory is applicable, but it can also be maybe because the tunneling theory is not entirely correct. So this is motivating, of course, us to look more into this tunneling theory And also, it's of course motivating that it's the initial key process in many strong field physics works. So now I will have a few slides where I try to guide you through some of the argumentations, or some of the thoughts you need to do. Yeah.
So, but I mean, experiment also directly ionizes the electrons, right?
Yes.
So, but if the theory does not include that, can it have a full picture?
No, I mean the experiments. Yeah. So the field. Yeah. So the experiments. Some of these are performed in circular polarized light. Some of them are performed in linear polarized light. That's already a complication. In the linear polarized light, we have rescattering. In the circular, we have no rescattering. So therefore, I mean, you have to do more than just considering the rate. But at least you have to get the rate correct before you can build more theory. And now, if you
Rate
have
for
the rate for
ionization.
ionization, yeah. So that at least has to be correct in order to have the correct final result. And now the question is also whether the experiments are performed in a regime where you have tunneling as a dominant ionization mechanism, or they are performed in a regime where there is some, you could say, non-adiabatic effects, or you could say maybe even over the barrier, because if the field is strong enough, there is no tunneling barrier to tunnel field. So now I will give you some. Yeah.
May I ask what keeps the molecule alive?
Yes, this is a good question. So the question was what aligns the molecule or what orients the molecule. There are many techniques. If now it's a polar molecule with a dipole, you can just apply a static field and use basically that the energy where you have this dipole, where you have the dipole aligned with the field, is the one which leads to the smallest energy. If it's not a but then maybe you don't want to do that, because then you don't have the molecule under field-free conditions. Then you can apply some pulse and do what is called, in the case of alignment, you can do impulsive alignment. This means that you create a coherent rotational wave packet, and this can also be done. So there are a few techniques that we can do. In Aarhus, Henrik Stapelfeldt, who was the leader of the experiment, or who is the leader of the experimental lab that perform these type of experiments, he has a lot of techniques for doing alignment. So now I want to come back to the theory. So now there will be some technical things, and this is the main paper that we have worked on, and you may find it odd, why should I stress one of my own paper in a graduate school? Well, the fact is that no one else has done the tunneling theory correctly for a molecular system. So I couldn't mention anyone. So we did this correctly for the first time. If you want a more pedagogical introduction, with a student some years ago, we actually unfolded this problem of Landau Odysseus. So we took that problem and wrote it out. So this is maybe worth publishing, or trying to. So we published that in this pedagogy. So this you can maybe also, if you like, you can have a look. So this is of course easier to read than this one, but this one only works for atoms. So if we start with hydrogen, here is our tunneling problem again. There is no way to treat this tunneling problem without having some kind of 1D motion asymptotic. You have to have some 1D motion, otherwise you can't design a tunneling theory. You have to have a 1D motion for the tunneling electron. And this you can do for hydrogen, because for hydrogen the problem separates in a particular set of coordinates which are called parabolic coordinates. And what do I mean by separation? I just mean that the solution can be written as a product of functions of eta and psi and phi. And of course, maybe you don't know the separation in this particular set of coordinates, but you definitely know separation in spherical coordinates. So this is now